Very good, very good afternoon. This is Morgan, Assistant Professor, Department of Agriculture Engineering, Sri Shanmugha College of Engineering and Technology. So today I'm going to discuss about the topic open channel flow. So earlier we discussed about what is open channel flow, what are all the different types of open channel flow and channels, and what are the basic definitions in open channel and the comparisons of open channel and pipe flow that we have discussed on the last session. So today I'm going to discuss about how to calculate the discharge with respect to the following equations. So we have discussed open channel flow with a free surface which is exposed to atmospheric pressure. In case of pipe flow, full pipe flow under hydraulic pressure. So discharge through open channel. So Chess is constant, Manning's, Basin's formula, Cotter's formula. So these are the major equations which we use to calculate the discharge through open channel. So discharge through open channel by Chess's formula. Here the diagram shows the uniform flow in open channel. We have two sections, the section 1-1 and section 2-2. The section 1-1 in the upstream side, the section 2-2 in the downstream side. We have in the section 1 in the upstream sides we have a slope. In the down we have steeper slope. In section 2-2 in the downstream side the don't have slopes. So the forces which is acting on the water between the sections 1-1 and 2-2, the component of weight of water, that is W into sine I, the frictional resistance that is opposite to the flow that we have calculated is F P L V square. So where the weight density is equal to density into volume. The density is rho, volume, area into the length of the flow. We are equating the two forces on both sides. So one is about the weight of water acting downward. The another one is frictional resistance. So FPLV square is equal to WAL sine I. So when I'm equating this, we will get the, I think previously, we will get the formula V is equal to C into square root of M sine I. When I'm equating the equations 2 and 3, for the small values of I, the sine I, that is at equal to 1. That is theta is equal to 90 degree, the sine 90 degrees is equal to 1. So sine I is equal to tan I is equal to I. So from this equations, we are replacing sine I by I. So where the velocity of the flow, where V is equal to C into square root of M I. So this is the velocity equation with respect to chassis. And also we know that the equation, according to the continuity equation, the discharge equations Q is equal to A into C, means A into velocity V. So now the velocity of the channel with respect to chassis we calculated where V is equal to C into square root of Mi. We just involve this V equal to Q is equal to A into V, substitute the value of V. So the equations will become Q AC into square root of Mi. This is the discharge equation. Okay. So the velocity of steady uniform flow on open channel is given by the equation chassis, where V is equal to C into square root of Mi. What is M? M is the hydraulic mean depth or otherwise hydraulic radius. A by P, A is area and P is measured perimeter. So for the I, it's a bed slope. The formula for I is head loss due to friction by length, where C is equal to chassis constants. The value of the chassis will be given from 50 to 60 depend upon the surface, open surface channel. So if the value of chassis is not given with respect to friction and with respect to frequency, we can use this equation square root of A G by F. With respect to this equation, we can able to calculate the value of chassis constant if the value is not given in the respected questions. So for this, the dimensional formula for chassis is L power 1 by 2, T power minus 1. So to find the chassis coefficient, the following empirical formula can be used. The one is Manning's formula, Cotter's formula, Basin's formula. With respect to these three equations, we can able to calculate the chassis coefficient. So the Manning's formula with respect to chassis, where C is equal to m power 1 by 6 by n. When I'm substituting the value of C in the above equation, we will get the discharge means velocity formulas. V is equal to 1 by n m 2 by 3 I power of. This may be the equations we used to get when I'm substituting the V value in discharge equations, where Q is equal to AC. So A into V, where V is in terms of Manning's 1 by n into m power 2 by 3 I power of. So where Q is equal to A into 1 by n m 2 by 3 I power of. So next is Coulter formula. So here the value of C in terms of Coulter, where C is equal to 23 plus 1 by n plus 0.00155 by S naught. So divided by 1 plus 23 plus 0.00155 by S naught into n by square root of R. Here the n is nothing but Manning's coefficient. R is mean hydraulic depth, that is M. M is equal to A by P. Mason's formula, where C is equal to 87 divided by 1 plus m by r, where m is a coefficient which depends upon the surface roughness. Either the surface is made up of concrete or masonry, or if it is an earthen material. Depend upon the type of surface roughness, the m value depends. Next is about the conveyance factor. According to this equations, where Q is equal to AC in the square root of MI. So where K is nothing but conveyance factor for open channel. So the where K is equal to AC into square root of M. So where Q is equal to square root of K into square root of I. The K factor is nothing but AC into square root of M. Accordingly, we just have the form problem. Find the rate of flow and conveyance for a rectangular channel 7.5 meter wide for a uniform flow and a depth of 2.25 meter. The bed slope of the channel is 1 in 1000 and chassis constant is given as 55. Also determine the type of flow. Here the rectangular channel, the wide has given 7.5. The uniform flow depth of 2.25 meters is given. The bed slope is given as 1 in 1000. And also the chassis constant is given as 55. So with respect to this all given data, we should calculate the rate of flow, that is discharge, and conveyance factor, that is K. With respect to the value of discharge as well as conveyance factor, we should find out the type of flow. Type of flow, it seems that whether it is a critical, subcritical or supercritical. So now I'm going to calculate the rate of flow as well as conveyance. So the breadth of the channel is given, that is width, and depth of the channel is given. It is about 2.25 meter. I is 1 by 1000. C is 55. The area for rectangular is BD. So B is 7.5. Depth 2.25. Multiplying these two, we will get the value of 16.88. Perimeter. So B plus 2D. The water touched portions is in the channel. We can say it is perimeter. For the perimeter for the rectangular section is B plus 2D. B is width. That is 7.5. Plus 2 times of depth, that is 2 into 2.25. We'll get perimeter as 12, where m is equal to A by P. Substitute the value of A and P. We will get the value of m is equal to 1.41 meter. Then the discharge formula, where Q is equal to AC into square root of MI. When I'm substituting the value of A, M, I, so we just get the value of Q is equal to 34.86. With respect to the value of Q, we can calculate the conveyance factor K, where Q is equal to K into square root of I. So Q is known, I is known. So where K is equal to Q divided by square root of I. The Q value is 34.86. I is 1 by 1000. You can substitute this value. You may get the value of K. The conveyance factor for the given rectangular channel is about 1102.41. With respect to the data, we calculated the discharge as well as conveyance factor. Now I'm going to calculate the type of flow. Here it is completely focusing on the gravitational. So we are using Froude number. So the Froude number Fr is equal to V by square root of G into D. The D is nothing but depth, where V is velocity. So velocity with respect to chassis, where V is equal to C into square root of Mi. The C value, M value, I value, all is given. You can substitute all this value. We may get the value of V is equal to 2.06. Let's substitute in this equation, that is D. Either we can use the depth of flow or either you can go with hydraulic depth, that is A by D. Then you can go with the depth of the channel, it is about 2.25. So 2.06 is the velocity, G is 9.81, D is 2.25. Let you can substitute all this value. The value of fluid number you get it is 0.44. The value is it is less than 1. So if the fluid number is less than 1, it is subcritical, equal to 1 critical, greater than 1, it is supercritical. So this is the another model. So next we'll move on to energy equation. So energy equations, it is a steady varied flow in a channel. The total energy hit at any point A at a depth D below the water surface. Here there is a section 1 and section 2. The section 1 is an upstream, section 2 is a downstream with a slope of Z. So we need to calculate the total energy hit at the point A with respect to the depth D. The equations will become H is equal to ZA at the center, ZA plus D cos theta plus alpha V square by 2G. So the energy equations will become H is equal to Z y cos theta plus alpha V square by 2G. So now this is the general equation with respect to the point A. So now I'm going to calculate the total head with respect to the section 1 and 2. For 1, the equations will become H1 is equal to Z1 plus Y1 cos theta plus alpha 1 V1 square by 2G. For the section 2, H2 is equal to Z2 plus Y2 cos theta plus alpha 2 V2 square by 2G. So with respect to that, if the channel is having the slope is very small, the theta will become very minimum. So where cos theta is equal to 1. That is cos 0, 1. So if the section is, a normal section is same than of the vertical section, the total energy at the section is H is equal to Z plus Y because cos theta will become 1. So Y plus alpha V square by 2G. The total energy of the channel flow with respect to the datum is given by H is equal to Z plus Y cos theta plus alpha V square by 2G. If the datum is coincide with the channel bed, if there is no slope or bed slope in the channel, so the expression, obviously the Z will become 0. So the equations will become E is equal to Y cos theta plus alpha V square by 2G. Let can substitute the value of cos theta is equal to 1. So the equations will become E is equal to Y plus alpha V square by 2G. This is the specific energy equation. This is the condition for specific energy with respect to critical depth. With respect to this, the value of condition for critical depth is Q square by G is equal to AC Q by T. With respect to this condition of specific energy, critical depth and true number, we have arrived at the specific energy equations for rectangular section with respect to the condition. The condition for critical energy is Q square by G is equal to A cube by T. With respect to this condition, we have arrived at the specific energy, critical specific energy for rectangular section is about 3 by 2 times of YC. For critical depth, YC is equal to Q square by G, the whole power 1 by 3. So we know that the fluid number, where fluid number FR is equal to V by square root of GY. So this is all about the discharge and specific energy equations for open channel. And thank you. We will discuss the remaining specific energy equations with respect to the problems and other things. We'll discuss in the next session. Thank you.